We didn't really get through everything today, and I apologize for that, but today will be not too long of a lecture. It'll just kind of cover the remainder of what I feel will give you a good understanding of at least what one of the major thrusts is on kind of understanding mechanisms of electrochemical reactions. So without further ado, I'll kind of tell you a little bit about, just remind you kind of where we left off last time. Right? So it's been about a week, let me just remind you, right? So, and the reminder really comes with what are all the processes that are occurring at an electrode solution interface that are giving rise to the current, right? And so remember that we had basically a scheme that looked like this, where we said if there was some reaction we wanted to do, we knew that that reaction could have a certain thermodynamic potential deliberately drawn here as 0. That would be true for, say, the hydrogen electrode. Making protons into hydrogen would occur by reference at this 0 value, or sorry, wouldn't occur. The thermodynamic potential is in fact 0. And so if we polarize beyond that value, we have these multiple regimes. Just so I'm going to remind you of these, right? If we have very low driving force or overpotential, we would expect a relatively low current. As we start to increase that overpotential, the current begins to rise, but in the limit that the current that's flowing is comparatively low, relative to the rate of flow of reagents to the electrode, in this case, say, protons, if we're hydrogen evolution, we still denote this as a region where we have activation control. And that's so critical, right? Because this region, or this type of data, to the extent that we can make sure our data is activation controlled, it gives us insight into mechanism, right? Because if we instead examine kinetics under conditions where there's a lot of transport control, we're simply probing the rate of the transport, which is an important consideration, an important engineering consideration, but does not really get down to the fundamental chemistry. So there's different regimes where we have mixed control, transport control, and then activation control, right? As you might imagine, depending upon the reaction you're doing, the current on the y-axis that will cause you to transition between these regions will be different, right? If I'm doing hydrogen evolution where my donor is water, in 55 molar water, right? There's a lot of it, and it's going to come to the electrode fairly rapidly. As a result of that, I can sustain a very, very high current before I induce any mass transport limitations, right? But say I look at O2 reduction, another reaction we'll examine, right? The fuel cell reaction. There we're reducing O2 to water, and the reactant in that, one of the key reactants, right, is O2, right? But the solubility of O2 in water is pretty low, right? On the order of about a millimolar, half a millimolar, depending upon the electrolyte strength. As a result of that, right, the transport limitations for O2 are going to set in at a much lower current than the transport limitations for, say, making hydrogen. Does that kind of make sense, right? It's just we have less of it, so it's going to be more quickly depleted, right? And in fact, you'll find that the transport limitations, even on an electrode where you're deliberately spinning it to increase the rate of flow, will often limit on the order of sort of 5 or 6 milliamps per centimeter squared, depending upon the pressure of O2 in the headspace. But for hydrogen evolution, you can go to tens to hundreds of milliamps per centimeter squared and not really have any transport limitations. It's simply because of the concentration differential between the two species. Okay. So I talked about this, and then of course there's other components to the current which are double layer capacitance, and this is why we typically collect kinetic data, though in not all cases, at steady state, so that the charging of the electrode is essentially finished by the time we measure the kinetic rate of the reaction. Okay, so let's consider how this, well, first off, we discussed this very briefly last time, which is that if, in fact, we have a reaction that is driven irreversibly at the electrode by virtue of the fact that the overpotential is significantly beyond 0.1 volts, that essentially means that by virtue of the reaction being downhill by this value, we essentially can assure ourselves that it's this reaction and that there's no contribution from the back reaction. Same would be true if we were, for example, driving O2 reduction with that overpotential being greater than 0.1 volts. In that limit, right, we know that the current that we're measuring at the electrode at steady state, this is critical at steady state, is simply related to the velocity of the reaction, or in this case, the rate molecules of O2 produced per unit time, per second, times the number of electrons that are transferred times Faraday's constant, right? And so this proportionality is essentially gospel as long as you've done everything you need to do to verify that you're not limited by transport or you're not limited by, and for example, the reaction is irreversible. And if you do this, you can generate data that looks like this, where you essentially plot on the y-axis overpotential and on the x-axis current. Remember, this is this funny plot where good catalysts are over here and bad catalysts are over there. The reason is that up here we have low current and high overpotential. Here we have high current, low overpotential, right? So this is the kind of data you get, and why exactly does this have this relation? It's related to Marcus theory, where essentially you have a reactant and a product well, and your catalyst defines the activation barrier. By virtue of setting these two wells and their bottoms at the same energy, I'm denoting that this reaction is right now at eta equals 0, right? Does everyone appreciate that, right? The thermal chemistry of this reaction is set to 0, and notably, the thermal chemistry is denoted by the position of these wells. So this is a situation when I've applied no overpotential, but as I apply an overpotential, I'm essentially raising the energy of either the holes or the electrons in the electrode. As a result, that's raising up either the reactant or the product well. It just depends on what the reaction is. And as a consequence of that, what I'm doing is translating some of this overpotential into a lowering of that activation barrier. And since the activation barrier is related in a logarithmic fashion to the rate constant, we get a log linear scaling between the overpotential and the rate of the reaction. So this comes fundamentally from the fact that activation barriers are log-wise scaling in reaction rate. And electrochemistry allows us uniquely, in a way that very many other methods, really no other methods, allow you to easily do, which is to tune that activation barrier by changing the reaction driving force. And that's really the power, right? This is why we're able to take the exact same reaction with the exact same material in the exact same medium and simply turn the dial on our potentiostat and vary the reaction by 3 orders of magnitude or 1,000-fold, right? There's no other way to do that without varying the thermal chemistry of the reaction. And that's what we're doing. Okay. An important feature of this that you'll analyze, especially in the latter portions of this lab, is what the slopes of these plots are. And what that can be used, what that tells you about possible mechanisms that are viable and which mechanisms are not viable. Right? So in mechanistic studies, we don't prove mechanisms, but our mechanistic data allows us to exclude possibilities, and by virtue of exclusion, the ones that remain are the mechanistic models that are the most reasonable. Doesn't mean they're the ones that are proved, they're just the ones most consistent with the data. And with more data, we could have even more refined mechanistic models. Okay. So let's consider actually an example of what the predicted electrokinetic behavior would be for a given mechanistic sequence for a reaction all of you are going to work on in this lab, which is this simple case of hydrogen evolution. Even the simple reaction, you can figure out, you can appreciate in a moment, is actually very kinetically complicated. So what is the reaction we're doing, right? So the reaction we're doing is taking electrons and protons and making H2. It's been known from independent studies that the rate of this reaction, or the log of the current at 0 driving force, that's a hypothetical value, right? At 0 driving force, realistically, you're not going to get any current. But if you back extrapolate the TAFL data to 0 overpotential, you can determine what's known as an exchange current density, and that's what this value is. Suffice it to say, for this example, all it is a measure of activity, with higher on this plot being higher activity. And this has been correlated to the strength of the surface metal H bond. And that would imply that a surface metal H bond is a viable intermediate when you convert protons to H2. And this is not too surprising, right? If you want to have a surface catalyze the reduction of H plus to H2, at some point you have to bind the H plus to the surface. That's what this is telling you, the strength of that bond, right? Okay. So let's consider an arbitrary metal surface. I've colored it for no particular reason. But say, in fact, it involves transfer of an electron and a proton to make that surface metal H bond, right? I'm particularly being agnostic as to the nature of the surface structure here, right? What faceting, what surface termination, what defect chemistry, those are all still very much the subject of contemporary debate and investigation. But it doesn't actually matter for this discussion, right? We can learn a lot about mechanism without knowing elements of that. So what I'm simply denoting is that a possible mechanistic step, we have not done any proof here, but a possible mechanistic step is one in which you have a surface site that picks up an electron and a proton and they can absorb H. Then I could pick up another electron and proton and have that second proton essentially react with the surface H. And as a result, we would have a net transfer two electrons and transfer two protons to make H2. Right, this is one viable mechanistic sequence. An alternative mechanistic sequence is you have another metal H that's at some other site on the surface, and they simply combine by diffusing to each other on the surface until they liberate H2. Does this mechanistic model make sense, right? So these are just some possible things to consider, right? By no means all of them, but some possible ones, right? Okay. So what would be the rate law, or what would be the rate expression we would predict for a rate limiting step that involved this sequence? So what I'm postulating is that this is the overall mechanistic sequence. I am being agnostic as to whether it goes down this pathway or this pathway, because what I'm presupposing in this mechanistic sequence is that this is determining the rate. And by virtue of this determining rate, on some level can't really, it doesn't make sense to talk about which one of these is relevant, because I'm blind to it and it doesn't determine the rate. So if this is rate limiting, right, we can write a rate expression based upon the derivation that I gave earlier, which is that this is an irreversible one electron transfer by virtue of it being rate limiting. As a result of that, the rate of that reaction will be related in an exponential fashion to the driving force, the overpotential, and this term beta, which is related to the symmetry factor. Remember, we did a very quick derivation of the symmetry factor last time as the first derivative of the Marcus equation. Did I do that? Maybe I didn't do that. Did we do that last time? No. Oh, sorry. Okay. For right now, we don't need to know that. All we need to know is that not all of that energy goes into lowering the activation barrier. Only a fraction of it does. I'll give you a little, I'll give you some reading material that I'll put online. That if you want to, you can read more about how you can explicitly derive what you would expect this to be. But suffice it to say, it can depend a little bit on the nature of the surface, but typically values of beta are on the order of about 0.5. And it would take me another 30 minutes, but I could do a discussion of why. What this is basically saying is that when I apply 100 millivolts, not all of that 100 millivolts is going into lowering the activation barrier. In many cases, approximately half is. And that's what this value is. If the value is much closer to 1, it means all of that 100 millivolts is going into changing the barrier. If it's much closer to 0, it means very little or none is going into changing. For irreversible electron transfer reactions like this, typically beta values are found to be around 0.5. And that can be derived, at least for outer sphere reactivity, using the Marcus equation. I'll put some stuff online to show that. Okay, so this is describing the exponential term. What is describing the rate, though, right, is this is telling you about the rate constant as a function of potential or overpotential. But because there's a proton involved in here, unsurprisingly, there's a dependence on proton, right? This is very simple. You have a reaction, involves a proton, so it's first order in proton, right? It's also dependent on this funny term here, which is a theta, and I've denoted theta sub m. Theta refers to essentially the surface concentration or surface coverage of the active sites that may be able to do this reaction. The reason I'm doing this treatment, right, is that there's no guarantee that every metal surface site here can bind the H. But we know some do by virtue of this reaction occurring on this surface and on any metal surface, or any material per se. Right? Now, obviously, if you design a better catalyst, what you may be doing in that design is altering this concentration, or altering this scaling here. But we want to know is which one's happening, right? That's the purpose of mechanistic investigation. So if we do this, right, this is telling us the rate of the reaction. We can turn that into a current by simply noting that there are 2 electrons transferred in the overall process and Faraday's constant, right? In other words, this V times NF is going to give us the J, and that's all we're doing in this substitution. So how do you determine the Tafel slope? Remember that the Tafel slope is the derivative of that plot, right? It's a plot of overpotential with respect to the log of the current. So the partial derivative of eta with respect to log J, or log current, is going to give us the Tafel slope. The great thing is we have an expression here for J as a function of eta. So simply taking the partial derivative of this will give you this expression. You can work through the math. It's not too much manipulation. Right? And what you determine from this is essentially the slope that you would expect if you take beta to be equal to 0.5 of this plot, if this were the rate limiting sequence. Now the data I showed you, which was real data on the last slide, was not at all this value, right? It was 60. And you can prove to yourself that varying beta, even between say 0.4 and 0.6, will cause some nominal change in the value you get for this slope. But there's a very big difference between something that's 150 millivolt per decade Tafel slope and something that's 30, right? And you can realize that, right? Because you can never have a beta value for a microscopic step greater than 1. And the limit of it being 1 would lead to a 60 millivolt per decade slope. In fact, there are no examples in electrocatalysis of a beta ever being really significantly above, I would say, probably 0.6. So that kind of gives you some bracketing on what are the ranges of scaling you can get for a sequence that involves an irreversible electron transfer in the rate limiting step. One other simple question, right? What would be the reaction order in proton? 1, right? That's not your question, right? So if I varied the pH, right, in other words, changing the proton activity, I would be able to use that to determine whether or not this hypothesis was correct, right? Or we may learn other things, right? We may change the pH and find, holy crap, it's second order in proton. This would cause us to alter our mechanistic model, right? So just to show you, there are catalysts that behave like this. For safety reasons, you probably won't be working with mercury in the lab. But mercury happens to be one of the materials that does this. In fact, the reason it's called the Tafel law, or the Tafel equation, you could say, is because Julius Tafel in 1905 accidentally stumbled upon this result. He was trying to do work with mercury electrodes, and he found, surprisingly, that when he did hydrogen evolution on them, they gave this very, very reproducible, around 120 millivolt per decade slope over a very, very large range, right? This is about 5 orders of magnitude and about 500 millivolts in overpotential. He was shocked, right? And of course, this is 1905, right? This was before Marcus theory. It was before modern inorganic chemistry. It was before the nanoscience revolution, right? Like nothing was known about how these surfaces behave, how electron transfer occurs. So this was purely a phenomenological result. But Tafel was credited with this because he didn't notice it and showed that it was reproducible. And I can't guarantee you'll get this because of the vagaries of the material that you make, but on materials like mercury, you can actually prove to yourself that you can get this data to these types of error bars, right? Very, very, very small error bars on this value for what is ostensibly a pretty complex material. Okay. I don't want to make this too long, but I just want to go through a couple of other possibilities mechanistically, right? So say, for example, instead, this was a reversible reaction, and this was the rate limiting step. So we're just going to run through a quick derivation on how this would be different, right? So how do I write any rate law, right? When I write any rate law in a multi-step sequence, the strategy is always the same. I begin with the rate limiting step, and I write a rate expression for that. Then I rewrite those terms in that rate limiting step in terms of the starting materials or the resting states of the catalytic cycle, right? We're going to do the same thing here, right? So the second step, this K2, denoting reaction 2, the velocity of that step alone is related to some rate constant. Again, the activity in proton, right? Because proton is involved here. Now I put in not theta m, because I'm not interested in the number of metal sites, but I put in theta h. I'm interested in the surface population of these H atoms, because that's the reactant in this step, right? Does that make sense? As a result, right, I have K2, that surface coverage of H, the activity of proton, and an exponential term that's related to this, again, the symmetry factor, because there's an electron here, the overpotential F over RT. Now my problem here, right, is that I can't independently measure the concentration of H. the surface H, right? So I need to rewrite that in terms of the preceding equilibrium. And the way to rewrite that is to simply note that the theta m, the sign pH, are simply, if you will, products over reactants, right? And that's simply given by the Nernst equation. Because it's an electrochemical equilibrium like any electrochemical equilibrium. And I just haven't shown all the math here, but you can work it out for yourself to convince yourself that that's going to relate to a potential independent equilibrium constant. Again, an activity in proton, right? If I have more protons around, it's going to move this equilibrium to this side by Le Chatelier. And if I have less, it's going to move it back, right? And an exponential term, but note here in this exponent, there's no beta, right? Because this is not an activated charge transfer. What we're saying is protons bind to the surface and come off millions of times before any one of them goes this way. So the barrier to this reaction, both for the forward and reverse, is extraordinarily small relative to the barrier for this reaction. As a result of that, this just goes back and forth and back and forth and back and forth, and it's in unconditional equilibrium is what we say here, right? Relative to the rate of this process. And as a result, the beta doesn't matter, right? Because the barrier and the shape of it doesn't matter because you're essentially just in equilibrium. And so if I change the driving force for this overall reaction by 60 millivolts, I'm going to vary the population of surface H relative to unbound H by 1 order of magnitude. And that's just the term that comes from it. So I have an expression here to be able to rewrite this in terms of now that theta n, right? A constant in the overall reaction. And as a result of that, I still put in the 2F because it's still 2 electrons in the overall process. But importantly, right now, I'm doubly dependent on the proton activity. If I increase the proton concentration, I get a bonus, right? Because not only is that driving this equilibrium towards product, and that's good anyway, because that increases the number of reactants for the second step, it also intrinsically increases the rate of the second step because I've increased the concentration. So when I change proton, I get a second order boost, because it's affecting both of the steps. The same is true for the potential dependence, right? Every time I change potential, that's going to alter the position of this equilibrium and affect the driving force and therefore the rate of this reaction. So when I alter potential, this numerator term is larger. It's not just beta as it was in the previous slide. It's 1 plus beta, the 1 coming from the fact that it's altering the position of this equilibrium. And if you work out the math here, right, this is a radically different Tafel slope than what you observed before. And that's simply because now, for every increment in voltage, I'm getting a double bonus. One of the bonus is coming from altering this position. A second one is coming from altering this rate. And that makes a better catalyst, right? Because remember, if the slope is lower on that plot, I'm able to get to higher current with lower driving force. So this is a good feature and a feature that's common to certain catalysts. And you're going to look at this in the systems you examine as well. Right? Okay. There's another piece here that's going to complicate this matter a little bit, and I apologize for this being cut off, but there's a proton here. So same sequence, but I'm now denoting. So I did something in the last slide that I didn't highlight, which is I'm deliberately saying in this sequence. Note how I'm drawing these arrows. What does this mean? Where does this live? Which side of the equilibrium does it live? Go to the upper. Yeah, right. So I'm drawing this deliberately to indicate that this is what's known as in minor equilibrium. Right? So have you guys heard this term before, minor versus major equilibrium? So in a catalytic sequence, when you're talking about a step, right, that's in equilibrium, it's not sufficient to simply say it's in equilibrium. Because what matters for the kinetics is whether or not it's in minor or major equilibrium. Major equilibrium would mean that the products are favored during the steady state catalysis for this equilibrium, and minor equilibrium would say the reactants are favored. If I were to take a snapshot of the surface, I'd see one part in maybe 1,000 that happens to have an H on the surface. I don't have a microscope that's that sensitive, but if I could do that, that's what this sequence is saying, right? And that's saying that the majority of them live here. But when I change the potential, right, I'm changing the fraction that live here. Does that make sense, right? In other words, you're going, when you change the potential, from 99.999 that are in this state to 99.99, right? You see what I mean? And then that change is changing this overall rate. Now, what if instead this resides in major equilibrium? I happen to have a catalyst that binds H's so strongly that by the time I'm in the region doing catalysis, the whole surface is packed with these H atoms. As a result of it being packed with H atoms, if it's already at 99.99% surface coverage, going from 99.99% of this species to 99.999% doesn't change the rate very much, right? Because I'm already packed fully. I can't put that much more to change the rate. Another way to say it is that in the previous sequence, this was the resting state. Now this is the resting state. Right? If I took a snapshot of the surface, what I'd see is hydrogens everywhere. And that matters a lot, right? And it matters a lot because now, when I write this rate expression, I do exactly the same thing I did before, because it involves a proton from solution and an electron. This expression is indistinguishable from what I wrote above, but I can approximate this value as essentially invariant over the potential scan that I'm doing. Right? Because it's already packed, and so it's essentially 1. And as a result, changing my potential doesn't alter this by any appreciable quantity, because this is already fully at a full coverage. Right? And that means I don't need to do anything more to rewrite this expression, and I recover a Tafel slope that was very similar to what I saw when it was just this step that was rate limiting. Now you might wonder, if I get this Tafel data or something thereabouts, how do I know whether it's this or the other one? Now, we won't have all the tools in this lab to be able to look at that, but you can look to some computation can help with this to understand what is the thermal chemistry of this, and spectroscopy can help with this, right? Because this is the resting state, we should be able to observe the stretching vibrations of these H's. And people have actually done this to ascertain whether or not there's a high or low population of these absorbents. We won't necessarily be able to do that here, and so one of the things you should realize, right, is that the mechanistic studies you do in the lab will not lead to unambiguous mechanistic determinations. In fact, no mechanistic study leads to unambiguous mechanistic determination because we don't prove mechanisms, right? But you will be able to exclude a lot of possibilities and leave certain ones on the table. And that's what this exercise is going to teach you about, because that insight itself is very, very valuable. Last thing here, right, real quick. We can do a sequence where this is still in minor equilibrium, but these recombine. Now, this is important, right? Because in this case, the rate of this reaction, which I'm denoting V3, is related to the surface coverage of this H squared, right? Because there's 2 of them coming together. I still have the same equilibrium expression that I had above for this step. And as a result of that, what I get is an expression that now has a second order dependence on that proton, and now not 1 plus beta, but just a value of 2. Right? Because the potential is not influencing this step. There's no electron in this arrow. There's no electron transfer here. The potential is influencing the step, and it's doing it with a full brunt of its force, if you will, by virtue of the fact that this is in unconditional equilibrium. So every time I change the potential, the only effect that's doing is changing the concentration of these surface sites. And because changing that has a second order dependence here on the rate of the reaction, that 2 naturally appears up here. What does this lead to? If you work out this, I don't get 40, I get an even lower Tafel slope. And in fact, this is the lowest possible Tafel slope you can get for a mechanism that involves 2 electrons being transferred. The best possible scenario you can have for any reaction in terms of a Tafel slope is 60 divided by the number of electrons transferred. So if I have a 2-electron transfer process like hydrogen generation, the best possible theoretical Tafel slope I can ever get is 30 millivolts per decade. If I had O2 reduction, like O2 to water, that had 4 electrons, it would be 60 divided by 4. The lowest possible Tafel slope I can ever get is 15. Now, Are there any catalysts that ever approximate this theoretical maximal limit or best limit? The only one we know about, and there have been 100 years of people examining materials, right, is platinum for hydrogen evolution. So this phenomenon only occurs, we know about, for one reaction for one material. And that's platinum doing the hydrogen evolution reaction, which happens to, in fact, display a 30 millivolt per decade capital slope, the lowest that is theoretically possible, and only for the hydrogen evolution reaction. For the oxygen evolution reaction, the lowest capital slopes that have been ever observed are in the ballpark of about 40. And that's a 4-electron transfer process, so it could go as low as 15. There's no material we know of. It would be great if someone in this room someday finds one, right? But there's no material that we know of, and it's still subject of contemporary research, right? Vibrant contemporary research, to try to find materials that have such low capacitance, but there isn't one for that, right? And we could talk at some other point maybe about theoretically why is it possible or not possible to get to such low values. But suffice it to say, this is the only material that does that. And I am now done with what I wanted to show you. So this gives you kind of an introduction as to how you think about reaction mechanisms for the hydrogen evolution reaction. You'll be looking at the exact same reaction just on materials that you create, right? And you'll understand from that, you know, that like the nuances of how to effectively do experiments to be able to put together mechanistic models. And the power you'll get from this is that you'll know how to then tackle even more complex materials, potentially for even more complex reactions. Okay, so with that, I want to thank you for sticking around for the second day and hearing about this. And I hope you really, really enjoyed this lab. It is a brand new experiment at MIT, and we really look forward to hearing your feedback on how it goes and how we can improve it, and on whether it really puts a sort of chemistry lens on important problems in energy analysis. Great. And again, I'll post this online, so you'll be able to view that, and Marius will have the video. So that's all I had. You guys can